The next set of methods we will look at are open domain methods. And like I said earlier, these methods are based on just choosing an arbitrary initial guess, not necessarily bracketing a root compared to closed domain methods, and just trying to converge to the root. If you remember, with closed domain methods, we had to be sure that our initial guesses bracketed the root. And that's not always easy without plotting the data. And of course, in many cases with scientific computing, we do not have access to visually inspect the function that we're solving for. So we need methods where we can just arbitrarily pick an initial guess and see if we can converge to a solution. And the first method is called the secant method, as an open domain method, and it's a very slight variation on the method of false position or regular falsy, in that it relaxes the assumption that the initial guesses have to bracket the root. So essentially it says, hey, let's take the regular falsy method, let's take the initial guesses, the initial brackets A and B, and let's not enforce that they should bracket the root, and let's see what happens. Just follow the same strategy. So here's an example, the same function given in this blue curve. We pick A and B now such that they do not bracket the root. And then just like the method of false position, you draw a line between A and B, and it gives you this point C as this new guess for the interval. Now, remember, with the regular falsy method, we had to bracket the root. In this case, we don't have to. So our new interval could be set in any way. So we can make we can keep A the same thing and then make C equal B, or we can make B the new A and C the new B. So one strategy to do this is to kind of go one step at a time, because A, B, and C are listed chronologically in that way. The next choice for the interval would be to make B the new A and to make C the new B. And therefore, B turns into the new A and C turns into the new B. And now we can check for the root f of C, see if it's less than the tolerance. If we hit the root, then great. Otherwise, we continue. And now we continue because obviously f of B is very far away from being 0. Now we draw a line between A and B and see where that line intersects the x-axis, and that's going to be our new C. Now again, the new interval is going to be B is going to turn be the new A, become the new A, and C is going to become the new B. And again, we draw a line between these guys, and that gives us the new value for C. The algorithm is simple. It's just a slight variation over the method of false position. Same thing, we given A and B arbitrarily chosen, calculate the slope, calculate the location of the point C, and then set the new interval, make B becomes the new A and C becomes the new B, and then check for convergence. If converged, return C, otherwise repeat. And here's an algorithm in Python for implementing this. Is just simply taking the method of false position and removing the if statement. Now the problem with the method of with the secant method is that it can get stuck in local minima. So that's a problem for the secant method, because it's not necessarily bracketing the root, and as the slope approaches 0, then you're not going to be able to get out of that local minimum. That's a well-known issue. So let's go ahead and open up the Jupyter notebook and go to the secant method. There's a little mistake over here. You have to change this regular falsy condition over here, and then we make A as the new B and B as our new C becomes our new B, and then just simply run it. So we're going to run this for U 0 equal 40 meters per second. Remember, M0 and T0 are still the same, and we call the secant method on R, the function f, and then we're just going to give it random brackets. Let's say so for the root, that's at 40, that's for the speed at 40, the root is over here. So I'm going to pick 2 points, 40 and 60, let's say, and see if we can converge to the root. Okay, we call secant with 40 and 60 and 1 e to the minus 5 for error and 100 iterations. and it did not converge. One of the ways this method fails and why it's not entirely robust. And in this case specifically, it's because the slope kind of sort of approaches zero very quickly over here. So it's going to throw the points very far away. So it looks like it feels like there's a minimum over here, although there's not. And so anyway, that's a great example that this method just kind of behaves erratically. And then there are no guarantees with these open domain methods.